Hi everyone, my name is Raheleh and I work at ADA. Our facilitators tonight are Gordon, Salman, and Royal, my colleagues who are all here. And we are covering a paper tonight by Uber-AI, a recent paper that just was published in arXiv last year. And it's accepted to ICLR, the International Conference on Learning Representations, and it's going to be presented in April this year. Okay, so at first I will start with an introduction to conditional language models. Then we will talk about the concept behind this approach in the paper, plug-and-play language models. And there are two control tasks, two control versions of text generation, one based on topic and one based on sentiment that we're going to cover. After that, we're going to have a 20-minute break and discussion, and we will come back with results and analysis, and after that, we will have a discussion. Okay, so let's get to it. We are all familiar with the transformer-based language models. The most famous and successful transformer-based language model was GPT-2 that was released by OpenAI in 2019. And basically, these language models are trained trying to predict the probability of a token given the previous token in the sequence. After these models are learned, we can use them for generation. You can give these language models this prefix, and they will generate the rest of the sequence for us. And okay, so is anybody here not familiar with transformer architecture or transformer models? So cool, okay. in a very simplified, brief version, transformers are blocks of self-attention plus a feed-forward neural network. Of course, there are more things like add and normalization on top of each layer, but assuming that you have a self-attention layer, and on top of that, you have a feed-forward neural network. And you can have blocks of this for this small model has 12 or 24 or even larger ones. The famous sentence that was, or the famous article about unicorns that was published by GPT-2 actually made everyone wonder, wow, these models can generate very accurate, like natural and very fluent text. So that was basically the big announcement and by a transformer-based language models in last year. We talked about how language models that are trained can be used to generate language. So given the prefix like the food is awful, then the language generation model can continue. The staff are rude and lazy. The food is disgusting, even by my standards. So that seems pretty natural and fluent. But what if we want to actually control the generation of the text to contain a specific topic? Or what if we wanted to have a positive sentiment to it, or negative, or any other attribute? That actually is the concept behind controlled text generation. And it has been shown that it's not very easy to steer or control the generation process toward those specific attributes. So for example, what if I have the same prefix as before, the food is awful, but I want to, from this point, turn the sentiment of the text and generate something positive after that. So something like, but there is also the music, the story, and the magic. How about that? This is basically the concept behind conditioning text generation. And there are several papers and several research that has already focused on this area. They can be basically categorized into these. Some of them may not, but generally we can have we can start from scratch. We can say we have a data set that contains a specific attribute. Let's say we want to generate positive. So we collect all the positive sentences, a large corpus, and start training a language model on this large corpus from scratch. So basically, the disadvantages of these techniques is that they require lots of computing resources. It's not that easy or practical to start training for every single attribute that we want from scratch train a language model. That's basically the issue with these models. The second category is that we say, okay, let's start with the pre-trained language model that we have, like something like GPT-2. And we try to fine-tune that model using a smaller data set that contains that attribute. That actually has been done, and there are papers about it. However, some researchers showed that this technique, because we fine-tune in a small data set, it might cause our models to face catastrophic forgetting. And eventually, the quality of the generated text might not be as good as the underlying language model. It might not be that fluent or natural. And the last set of techniques is that we just use the unconditional language model, like GPT-2. We generate the sentences, but in a post-processing manner, we go and try to replace some parts of the text with some engrams or phrases that contains that attribute, and we know those. Like, for example, if it's about a topic politics, we have some keywords or phrases that we know that contains those, and we try to force that into the output. And of course, that is not as strong as the first two categories, and they may have they definitely have less natural and less fluent generations in this category. So what is proposed in this paper, what authors propose here, is a plug-and-play approach, which means that we won't touch the underlying language model. We won't retrain it, or we won't fine-tune the weights. We just keep it as it is, but we will plug in an attribute model, and we will update I will get to it later, but we will update the latent representation in a way that it will generate the text with the desired attribute, with the target attribute that we're looking for. So assuming that we have what we are given is unconditional language model, we have access to that, it's GPT-2. If we have an attribute model, which means that given a sequence of text or sequence of tokens, we can predict to what probability, to what extent that text contains the attribute that we're looking for. So if it's about sentiment and we are looking for positives, generating positive sentiments, the attribute model can be a sentiment classifier. So we give a text to our classifier, and it says it has a probability of 0.6 to be positive and 0.4 to negative, if we are assuming only two classes. What we are looking for in our target is a conditional language model, which means that given the attribute, we want to generate a text that has that attribute. So if we say A is being positive, then given being positive, we want to generate text. So fortunately, we can follow the Bayes rule and say, OK, we want our target, we want a conditional language model. We will say that is equivalent to the product of the unconditional language model and the attribute model together. So now the question is that we need to sample from this distribution. We need to sample from this product. And there are sampling techniques like rejection sampling or MCMC, but it has been shown that these sampling techniques can be slow and not really applicable to this case. So the authors are inspired, the method that the authors applied in this technique, they are inspired by a paper that was published in Vision in 2017. It's called Plug and Play Generative Networks, and it's about generating conditional images. What technique they use is an approximation sampling technique, and it's called approximate metropolis adjusted land domain approach. And so, to briefly simplify it, it's not altered, but it is similar to following the gradients in the latent representation space. And to basically better explain this in the next slide, and I'm just getting to it, is that OK, let's just go follow it. So how this is done in the PPLM language model, in the plug-and-play language model. We said that following gradients in the latent representation, but what it means. So we are given a prefix, and we can use the underlying unconditional language model to generate the to calculate the probability of this sentence, yes, using a language model. And then we also have the attribute classifier, attribute model, which is, let's say, sentiment classifier. We can also calculate the probability of this given prefix having that attribute. The ideal case is that we want to, in the next step, we want to have increase these probabilities. What does it mean? It means that if we can calculate these probabilities, and if we can calculate their gradients, it's just moving slightly with the latent representations of the underlying language model towards that gradient. So all that we need for generating language is the underlying unconditional language model. And calculating the probabilities of P of x and P of a given x, we will calculate their gradients, and we slightly move our latent representation in the direction of increasing their gradients. What will happen is that in the next step, what we generate is gonna contain, with higher probability, is gonna contain the attribute. It's gonna be a token that contains that attribute. So it's gonna be a positive token, for example. This is just basically a higher level of what is going on. We will get into the mathematical and implementation details in a few minutes. So this, yeah, sorry, go ahead. Yes.
Move back to the previous slide. And if I'm jumping ahead, feel free to answer it when it comes up. Does that mean, when you say compute the gradients, does that mean you want to use it as a cost function? Because that's one way. Okay.
Yes. That's it.
Nice.
Yeah.
So we have to decide what the ratio is between these two gradients as they move into our back prop. Is that right?
Yes. So
how do we?
You mean how much we want to optimize the attribute model, which is the probability of a given x? How much?
Losing some naturalness.
Yes, definitely. You're 100% correct. And there are two techniques that they use that I will get to it in a few minutes, and they ensure the fluency is not reduced or too much affected. Cool. Any other questions? Great. So I really like this figure in the Uber AI blog post. Actually, it kind of summarizes the whole idea in one picture, and very cute, and I really like it. So it says that imagine that the underlying language model, the unconditional language model, which is usually very large models, like billions of parameters, or lots of computation goes to train these models. So it's a mammoth. It's hard to move a mammoth. But what if we have, and we don't want to change a mammoth. We don't want to change weights in our underlying language model. What we do is that we have an attribute model, which is our small field mouse that is sitting on top of the mammoth, and says, I just control where you go. And how do I control it is just by calculating gradients of the attribute model. So if I'm calculating the gradients of the attribute model and I'm moving in that direction, I'm increasing the chance of creating sentences that contains that attribute. And so basically, this all says that having or training the mouse, the field mouse on top, is much easier than changing the mammoth, because the mouse has even very, very less number of parameters compared to the big mammoth underneath. So, yeah. Sure.
Relationship between the unconditional model and the attribute model.
Yes.
So from what I understood, the attribute model is a prior distribution. Is that correct?
It's not a prior distribution. The attribute model is a separate classifier that we trained. Let's say it's about sentiment, and we trained a classifier using IMDb reviews, for example. It's just a classifier. We save it. On the generation time, we only load that attribute model and plug it in to the underlying language model. It will affect the embeddings that this language model works on, but it won't affect the weights of the language model. And it's basically a classifier that has been separately trained. It can be anything. Any attribute model, you can use it. We'll go over some examples for topic, and that maybe help that to get that. Thank you. Okay, so far we covered the basically general concept behind it. Now let's dive into more implementation mathematical parts of the work. So language models with transformers, like how they work. When we train a language model, we are assuming that we are given a sequence of tokens, and what we are trying to predict is what is the probability of that sequence of tokens in the language that we are modeling. If it's in English, in English. So it is a product of the current token given the previous tokens. After we learn that, so like basically even in the way of learning this, how this implementation works, I said a little bit about like the transformers and that they are based on self-attention. The self-attention is nothing by just having 3 vectors, or basically in this case we only need 2 because the query is the token, but we have a two vectors for 2 matrices. One is called value and the other is key and value matrices. From the first token, or time step 0 to time step t, and all the layers. So if we have 12 layers of transformers blocks, then we have 12 layers. So all we need when we want to generate the next token or predict the probability of the next token is that history. So if we keep everything as we move on, if we call it h of t, which is a list of all these key value pairs from layer 1 to the last layer, from time step 0 to time step t, then all we need to calculate the next token is just this, plus the current token. Okay. So having that, we are given x of t, and we have the h of t. We pass it to our language model, and we get the h of t plus 1 for the next step. Also, we get a logit vector of the next token that we are trying to predict. So O of t plus 1 is actually the logit vector here. So using a weight matrix, or like the W here, we will map that logit vector to the length of our vocabulary, because we want to predict the next token. So W, like product of the W by the logit vector, gives us, after we apply softmax, gives us a probability distribution over our vocabulary. So we have a probability distribution over vocabulary for the next token. How you sample the next token? One simple way is that you say, okay, let's pick the maximum one, the word in the vocabulary that has the highest probability, and that's maximization. And people did that. Like, I mean, it has been used, the maximization. However, recent research shown that using maximization by sampling through maximization technique, you will usually get bland and strangely repetitive text. It has been shown by a work by Holtzman and co-authors, and it's called The Curious Case of Neural Text Degeneration. So something like if I give a prefix of I don't, it will generate I don't know, I don't know, I don't know, and go on. The same thing over and over. So the idea of top case sampling has been introduced. And this technique has been used in GPT-2. So GPT-2 actually used this for generating those fluent texts that we all seen before. The idea is that instead of maximization, let's apply randomization, but not randomization over all the vocabulary. What we do is that we first select the subset over that vocabulary that we have. So if our vocabulary size, let's say, is 3,000, for example, and K is 100, for example, I'm just like giving examples, then you will sort all the vocabulary based on their probability and take the top 100 and then randomly sample from that. that actually has been shown that it helps a lot to generating a diverse and fluent language compared to maximization. And one other thing is that also, it was very interesting that in the work by Holtzman, they showed that the probability distribution by maximization, if you plot the probability distribution generated by machine and then the way by human, like if you give humans to generate some text and then you plot the probability distribution, there's a noticeable difference between those probabilities. So actually that is another clue that maximization is not the best approach here. Yes?
Could you clarify on the previous slides
Sure.
the key and value vectors?
Yes.
Why are they called so, and what is this terminology related to?
Yeah, so it's key and value is the ones that are used for calculating self-attention. Self-attention is that when I want to generate an embedding for the current token in my sequence, which other token should I attend to more when I want to generate that? So like we have attention in encoder-decoder, let's say in machine translation, is that at the time of decoding, how much should I attend to the token at the time of encoding, which is the source language. But self-attention is that in the given sequence, we only have one sequence, how much should I pay attention when I'm generating the embedding for the current token? And the key and values are basically, key gives you like the importance of, so each token has a key when you want to generate the embedding for the current token, each previous or next tokens, let's say. And then well, in this case, it's only previous, but you have a key which shows the importance of that token generating the weight of this current token. And the value is the actual value, like it's that how much is important, but it will get multiplied by the value of that token. And then they will be sum up, and you will calculate the z value, which that z value will affect the embedding of the token, of the current token.
Do you mind if I plug in? No pun intended.
Pardon?
So just want to add a comment, if you don't mind.
Oh, no, for sure.
Maybe it helps. So very quickly, regarded as an RNN in a parallelized map. So don't get too much distracted with Ks and values, so on and so forth. If you want to know the details, there are 2 videos on our YouTube channel. Attention is all you need.
Yes.
As well as BERT. In both of them, we do get into the details of how it works. But don't be distracted for now, please.
Yeah.
Right?
It's just details of transformers underlined. Yeah. Sorry about it. Okay, so up until this point, which we talked about top case sampling and the previous slide, we are talking about how transformer-based language models work. But what happened to our PPLM, the plug-and-play language model, how that comes to play? So we are talking about steering the generation, how we can steer it towards the direction of our desired attribute. So we talked about h of t and said h of t needs, it's all we need when we want to generate the next token, which means that the update that we make to that list or that vector, that big vector, is basically the update that we need to push our language model towards the desired attribute. So how it's calculated? So we talked about the attribute model, which is the probability of A given X. We know that what generates X is h of t, and now in this case, plus the update, which is delta h of t. So if we rewrite that, then all we need to do is basically calculate the gradient with respect to the underlying latent representations, which is nothing else rather than h of t. We take the gradient out of that. The denominator is just the normalization factor. So we calculate the gradient, and we scale it with learning a step size. The alpha is the step size. And we update our latent representation. That latent representation is the latent representation of the given prefix. So if it was I don't know so far, and we wanted to generate the next token, that I don't know has an h of t, and we only update that representation. Again, I want to mention that we are not updating the weights of the language model, but just the embeddings of the given text. And So having that, like when we update that, which means that we are steering our mammoth towards the desired attribute, then we can give it with the current token to our language model, generate the next logit vector at time step t plus 1, and use that perturbed or new logit vector to create the next token. Okay. Sorry. No, yes.
So are you saying this calculation is discarded after you calculate the sample from the folder? So you don't need to calculate anymore, you're not actually saving it anymore?
So this calculation is that, okay, I have, I get to the sample in a minute. It's, for example, the chicken taste. That's my prefix token. I give it to my transformer language model, and then I get a hidden representation for that, yes? I give that also to my attribute model, calculate how much it is close to the desired attribute, calculate the gradient of that, apply that gradient to this representation. So I have a new representation for the chicken taste, yes? Use that new representation to generate the next token. But how do we know that is actually, like maybe this actually helps. It's done in 3 steps. So we are assuming here that the desired attribute is generating positive sentences. What we are given so far is the chicken taste, yes? So at the first step, we don't have anything else rather than our underlying language model, the GPT-2, the unconditional language model. We give this latent representation of the chicken taste to the model, we get a probability distribution of what should be the probability distribution of the next token. We sample from this. Let's say if we sample randomly from the top 5, we get OK. So the text that the unconditional language model was going to produce was the chicken tastes OK. But now we know that we have an attribute model. We give the chicken tastes OK to our attribute model. It gives us a probability of how positive it is. It's not that positive. It's not negative, but it's not very positive either. So there is some updates to the model. We calculate the gradient. And basically, the gradient is cross entropy. So you have 3 classes, very positive, very negative, let's say, and neutral, assuming. Then you know that your attribute model predicted that the chicken tastes OK is around neutral. So there is a cross entropy loss. You can calculate that gradient. You apply that gradient in a backward pass to update the latent representations of the chicken taste. Okay. If you update that in the direction of the positive values, now if you give again this latent representation to the forward pass and try to have a probability distribution and now randomly pick the next token, you get delicious. Is it now more clear? Any questions? Yes?
It seems that if you're still doing random sampling here, that you might need to go looping around a few times.
I get to that as well. So okay. It's actually, it's a very good question. So when you sample from this top case sampling, you get, let's say, after OK, let's imagine in the first run, we get something like good. They say that they have number of iterations, yes? They start from 3 and they go up until 10. In the experiments, they set it to 3. So in the next iteration, they update that. They give, then again, this representation, the updated one, and then they get great, let's say. And in the third iteration, they grade delicious. Or they have a few iterations that they move on. And after that, after the last iteration, whatever is generated as the next token will be fixed. So we have now the chicken tastes delicious. We will move on to the next token generation. So each token generation has number of iterations. Yeah. Okay. Yes.
Maybe that could be a clarification question. So your LM over there is a transformer layer?
Yes, it's our language model. Yes.
One transformer layer.
It's in this case they use GPT-2 medium, which is like 24. But you need all of those 24 layers when you want to generate the next token. And what you update is all the layers hidden. Yes.
Oh, interesting.
Yes. You update all the layers, all the steps back. Okay. You basically...
Sounds risky to me.
Yeah, you basically update the... Actually, as I understood based on, I was like looking at the code, you update the hidden representation of your language model so far, which is h of t, and h of t contains all the layers and all the steps. You update that with delta h of t, and that delta h of t is calculated by the backward pass gradients of the attribute model.
Yes.
Yeah. Yes.
As a sanity check for myself, is the magnitude of alpha that determines the level of deliciousness versus not bad?
So that, you mean here, the alpha,
yeah.
Yes? That's actually called a strength factor as well. Imagine that is a control knob. If you increase it, you are basically pushing your model towards that attribute, desired attribute more, yes?
Yeah.
And you probably get there faster regarding, but I will show how much you can increase, because after a while it might be too, like it will add basically repetitiveness and like noise to it. What I mean is that this alpha, if you set it to 0, you're basically using the unconditional language model, or GPT-2 in this case, to generate. Nothing will happen. No hidden representation is going to get updated. Yeah.
So you mentioned the number of iterations to get okay to delicious. Is it?
It may happen in the first iteration. I mean, it's just there's a fixed number of iterations. They don't check it. They say, okay, let's run it 3 iterations, and then we will move to the next token generation.
And there is no more sophisticated criteria than that, just...
Yeah. Thanks.
Can you take a question from online?
Sure, yes.
So the online question is, I think he's wondering how can a small model sufficiently know about the big language models latent space? Does that make sense? So the small attribute model knows something about latent space of the language model?
No, it's just the
repeat the question?
Oh, the question was that how does the attribute model, which is small, knows about the latent space of the big unconditional language model? No, it's just imagine that's a classifier, and you give it the generated text so far, and it says it's not positive. That's all it knows. Then we calculate gradients in the direction of the classifier, but we apply that gradient to our latent representation in the language model. So yeah, that's basically it. I hope I answered the question. Cool. Yeah. Yes, so ensuring fluency. What we showed here actually is all the gradients are with regard to attribute model. We calculate the gradients of the attribute model given the sequence. What happened to the P of X, to the probability of the sequence calculated by the language model? And it's very important, because if we only do this, if we only follow the gradients on the attribute model, what we will generate is great. Yeah, it can happen because it's all positive, but it's not fluent at all, and it's not natural, because we forgot about the probability of the underlying language model. So ensuring fluency, and this actually picture helps a lot, because it says that imagine that this is a very simplified version of the space and the latent space. If we move towards the left of the picture, we are in the area that we have lower probabilities for our attribute model. Assuming sentiment, these are basically sentences, space of the sentences with negative values. And as you move towards the right, you get higher values for your attribute model. So hopefully we want to be moved in that direction. However, the blue curve shows the space that our language model has fluent sentences. So if we don't consider that and start from the left dark circle, we might end up moving to the empty circle. That is an area that has a high probability for the attribute model, but is not fluent. It's not good for our language model. That's why we need to consider both and hopefully move to the middle one, to the middle dark circle. How we can ensure that? They apply 2 techniques. One is minimizing the KL divergence, between the unconditional language model, which is GPT-2 underneath, and the controlled version of it. So let's say we have a probability distribution after the chicken taste. We had a probability distribution over vocabulary for OK before we updated the latent representation. And we have another updated probability distribution that gave us delicious after we updated the hidden space. If we calculate the KL divergence between these two, then we are basically ensuring that the fluency of the text will be retained as well. And it will directly affect the update that we make to the hidden representation. But they also said that there is another technique that it used. They used actually both. And the other technique is that let's perform a post-norm fusion as well. Let's update our latent representation. Let's move on, calculate the logit vectors. When we want to sample the next token, we consider both probability distribution, the perturbed one, the updated one, and also the one by the unconditional language model. And with a scaling factor that usually is 0.85 or 0.9 towards the updated distribution, but we give a chance to the uncontrolled language model also to pick a token. Is it clear? Are any other questions now? Thank you. Go.
That just sounds very discrete. Maybe it's a discussion. Maybe
yeah,
it's
maybe.
A discussion.
Yeah, I had a, yeah. Sounds good. Before like the break, there is one more technique that actually they use, and it is not specific to the plug-and-play language model. It can be applied to any generation model. So you have a generation model, you generate R different samples, and you calculate based on your attribute, you calculate which one contains the desired attribute more. You rank them, then probably the ones that appear at the top are the best ones. However, there's another one which is called like sampling in here, or maybe that's not the reason we are sampling, but basically to filter samples that are not good. And that is, we want to pick the sentences that are diverse enough. So we calculate a score called distinct engram. It is basically the number of distinct engrams that appear in our generated text, normalized by the length of the text. And we have a predefined threshold. We say that the sentences that their score is lower than that threshold, we just filter them. So we have a ranking based on the desired attribute, and we have a filtering based on low diversity. This technique can be applied to any generation. It doesn't have to be only to PPLM, and it's basically you generate all the sentences and you apply that technique later, which they did. They applied this to both the GPT-2, the unconditioned or uncontrollable version of the language model, plus their own approach. Cool. Okay, so this was the mathematical detail about the plug-and-play language model. There are two versions of the control text that they did lots of experiment with in this paper. One is about topics. What if we want our generated text to contain a specific topic? And one is about sentiment. Now, what is their attribute model that they used for generating topic? So they use the bag of word model for topic, which means that if you have a topic, let's say politics in mind, you know that there are a few keywords or maybe a list of keywords that are very discriminative for politics. You generate that bag of word list or that list of the keywords, and what you use is that you say, what is the probability of the generated text being about politics? And it is the sum or the log of the sum of the probabilities of the fact that the next generated token is one of these. So you have, let's say, 10 for topic. It's a small number for a topic, but let's say 10 keywords for politics. You consider that. So when you want to generate the next token, and you have the probability distribution, the P of t plus 1 in time step t plus 1. What is the probability that one of these words are going to be selected? if you sum that probability together and take a log of it, you are getting the probability of your generated text being about politics. And about the sentiment, they basically say that it's a discriminative attribute model. It's basically a classifier that you train on a separate data set. It's about sentiment. So SST5 is a data set for sentiment. You are given label data. You have the text and you have the label, which is positive, negative, very negative, whatever, like the list of the labels. And you use a single layer classifier to train a sentiment classification on this, which is basically you give your input sequence of tokens, you calculate their embeddings, you take an average over that embedding, and you give it to your one layer classifier, which predicts for you whether the given text is positive, negative, or neutral, let's say. But that's basically like, it can be any classifier here for any attribute, but they work on two for their experiments. Okay, so if there's no question, I will wrap up this part of the session.
So I guess, go ahead. You might be asking what I was going to answer.
And you can mix the two topics
Yes.
and the discussion.
Yes, and lots of other attributes, so 4 or 5, you can mix all of them. Yeah? Yes.
Is there any compatibility between the attribute and the language model which has to be required in order for this scheme to work? The compatibility, you have an attribute model,
Yes.
and you have a language model.
Yes, correct.
Can I choose arbitrarily any language model with latent representation and any attribute model?
Yeah, it
just
can be
combine
any
them?
attribute model that's based on transformers, because this technique is the way that they update the hidden representations, like calculating the keys and values, and it's based on the architecture of transformers. But any attribute model, any model that gives you the probability of your text having that attribute, plus any language model which is based on transformers. Yeah.
I guess like theoretically for non-transformers as well, like if you have H, you can update it for
Correct.
RNNs as well. Like it should work. I haven't tried. Hopefully they did.
I think like theoretically yes, you may want to change like the implementation of the part, but theoretically like, the concept behind this plug and play, like that you don't touch the language model, but you kind of steer it towards the attribute model, should work with everything. But probably the code should be changed to work with the new language model architecture. Yeah.
So a quick emphasis. Oh, did you have something? If you go to the previous slide.
Sure.
Did you say mean? Yes.
Yeah.
So just get your keys and values and average them?
Yeah, exactly. Okay. Average over the length, like basically if you have 10 tokens, you average over 10, and then you give it to one layer.
Okay, we'll talk about it.
Yeah, yeah, cool. Great. I think that's it. Thank you.
There's one question.
Oh,
One more
sorry.
question. Yeah, sorry. I have a question about like how have you tried to see how the model performs on some I'd say like at extreme points, like when you for example apply it to the set of words which is absurd or even contradictory to each other, how does the model deals with it?
So applying it to, let's say, two different attributes, but the keywords are kind of the opposite of each other. Like
Yeah, kind of, I guess.
Well, I haven't, but I think that some of the experiments in the paper, and they've done lots of experiments, and they report all of those in the appendices, is that they consider different attribute models and some odd combinations even, and they show how the model still can generate text in that direction, although it may be twisted or funny or not accurate in the real world, but it actually generates that. However, I haven't tested it myself. Sorry.
Thank you very much.
No worries.
Do you think this method can work with sarcasm?
Yeah, I think that That is probably very difficult. To be honest, I started downloading a dataset from Kaggle for funny jokes and wanted to see if I can make something funny by this model. I wasn't successful yet, but but not because the model doesn't work. I didn't have the time to finish the experiment. That's why.
A follow-up question: is it is it easy to give this model an existing text?
Yes.
And perform some sort of minimal transformations on it to satisfy.
Like
is there such a problem
paraphrasing kind of task, or?
Yeah, I want to make my text funnier or prettier.
So like a style transfer?
I don't know what it's called.
Well, I guess you would have to train it. So you have to create the loss function and train it to that attribute, right?
Yeah, so you will have a classifier that says the given text is funny or not. Otherwise, you don't have attribute model. So assuming you have that, and then I would say you can start from the first 2 or 3 tokens of your actual sentence, and let's see how it generates after that. Or you can give it play with how many tokens you want to give as prefix and how many tokens you want to generate after that. Because you can define a fixed length. Let's say, okay, I want to generate 50 tokens after that, and it will generate for you. And it will get into the space that has that attribute, and even without updating the hidden representation, you can continue generating.
But it will generate new text in any case.
Yes. Yes. Yes.
So
thank you.
It's about the time. You can answer your question.
No, I was just going to clap.
Thank you. Thanks. Thank you.
So it's break time.
Can I just add something? So in addition to questions in this section, you can have argumentative, comparative questions. But please have her go through her entire points, and then we can start.
Welcome back. Let's start with the evaluation part of the paper. How and what points did the authors had in mind when they talked about the experiments and evaluation of the proposed approach? So there are 2 properties we are considering for evaluation here. One was that the main concept behind the paper, generating a text that has some attribute. So does the generated text contains that attribute or not? So that's one thing that they basically evaluated. And the other is that whether by this technique and generating text containing that attribute, did we affect the fluency or the naturalness of the generated text or not? So the fluency of the text is another property. How did it gather the evaluations? In two sets of basically steps. One is automatic evaluation. For fluency of the generated text, perplexity is one metric that has been used before for many years and is also has been used in this paper. However, when they wanted to calculate the perplexity of the generated text by PPLM or other baselines, they used a pre-trained model, and it's the GPT model, not GPT-2. So they mentioned that for perplexity, they used that technique or that pre-trained language model. And the other metric here is that when we want to see if we generated diverse language or diverse text as well, is do you remember before the break we talked about distinct engrams and how when we were filtering the generated samples that their score was lower than a threshold? That's actually the same score here. So we calculate the number of distinct engrams normalized by the length of the text, and that's another automatic evaluation metric. For the relevancy of the attribute, they did the human evaluation. So they had 9 annotators, and each sample was annotated by 3 judges or 3 human. For the fluency, they showed each individual generated sample or generated text, and they asked the annotators to label it from 1 to 5, 1 being not fluent at all and 5 being very fluent. And for the attribute relevancy, so let's say if the desired attribute was being positive or towards a specific topic, they annotated in an A/B testing manner, which means that they showed a pair of generated text, one from each model, and then they asked the annotators to label which one contains that attribute. They also told the annotators that they can label as both or neither. So it is both of the models contain the attribute, neither of them, or which one actually, if it's only one of them. Okay, so ablation study. The experiments actually has two parts. One is the ablation study, and the other is the comparison between different baselines, which is different previous work by other researchers in this area. So the ablation study, first, we have a model, we call it B. It's actually the baseline, and it is nothing but the original GPT-2. When we only sample once and we generate a text. The second one is called BR. It is the same as the B, but we apply sampling and ranking, which means we are using the original GPT-2, generate several sentences or general sequences of text, and then rank them based on their attribute value, and filter them based on low diversity score, and then we pick the best one. So the one that is above the threshold for diversity and is the highest in the attribute model. Then we have BC, which is the PPLM, but when you sample once. So you update the hidden representation, you use the PPLM language model, you generate a text, and that is your output. And BCR is the same as BC, but sampling and ranking as well. So you generate several texts by BC, and then you rank and sample. And the baseline that they use, or the approaches, yeah, so, sure.
So, third one I got, what's the final?
Sorry, can you repeat?
Sorry, can you repeat the question?
The question is, could you repeat the last two?
Oh, the question was to repeat. Okay, yes. So, sorry. So BC is the version, it's basically the plug and play language model that was presented in this paper. But when you use that technique to generate a text, yes. But we talked about filtering and ranking as well, and we say that technique to generate R samples, rank, and filter can be applied to any generation. What if we apply it to BC? Then we get BCR. So BCR is using the PPLM to update the latent representation, generate text, and then generate it several times, not once, but several sentences or several sequences of text, and then rank based on the attribute value, and filter the ones that have low diversity and pick the best one. Yeah. Cool. Okay. So next we have the other we have the same like conditional text generation, but other researchers that has been done over the past few years. The first one is CTRL. It is a recent conditional transformer, again, language model. It was released by Salesforce. What they did is that they had 50 codes. They set the number of codes, and the codes are like positive and review. Like it means that generate a text in the domain like of the reviews, like if you're writing review, and it be positive. Or by positive, they could even say what is the rating. And they had these 50 codes, and then they basically learned from their data set. So they knew which data set has that attribute, and when they learned or trained the language model on that, they learned the attribute. So in the generation time, they give the codes, and the generation will generate the text relevant to that attribute. Actually, this is a very large model. It's about 1.6 billion parameters model that they use in this. Yes?
So when they train the model on several different data sets,
yes.
Are the models trained on these data sets somehow coupled? For example, they have the same weights?
It's one model, but when they're training, they have codes. They know that this text is positive and it's about reviews. So like the code is fed into the model, and when the language model is trained, it knows that this sample is about. But this is only one model. They trained on 50. Oh, sorry.
You have 10 different sets of training data.
Yes.
You train one model 10 times. You get 10 parameterizations of the model, or the 10 instances of the models. Are these instances completely unrelated, or do they share, for example, anything in common like weights?
In which model? You are doing that with which model? With the PPLM, or this? Are you talking about this CTRL?
I think it's item 2.
Item
right?
2?
Oh, item.
I haven't covered item 2 yet. I'm talking about the first one, which is the CTRL. It was by Salesforce. And in that case, you only generate one. You can generate like multiple, and they mentioned in the paper as well. So it's a technique separate than this technique that we proposed. It's just a comparison with previous work. And your question is that whether they generate 10 different sentences using that model, the CTRL? Is that the question?
Sorry, as far as I understand, for the comparison, we need somehow to train the data to produce a desired attribute.
Yes.
In the samples.
They used the pre-trained model by this paper. They didn't train anything for the sake of comparison for CTRL. They just mapped. For example, they know that if they give the system, like they mapped they wanted to compare their generation of the text that has topic politics with this model, this baseline. So they knew which code to give to CTRL to generate politics data. They generated that. They used their PPLM version and generated text, and they just gave to annotators to label it. Yes, conditional language modeling. They didn't train anything. So the pre-trained model was released by Salesforce. They just used it to generate text. Make sense? Yeah. No training here. Nothing like whatever we see here as baselines. They use whatever is basically made publicly available by these papers. Cool. The second approach is actually a fine-tuning version of the language model. It's called GPT-2 fine-tuning based on reinforcement learning. And how they did it is that basically they say that assume that we don't have any labeled data set to fine-tune the language model. Their target is to generate positive sentences, just positivity. What I say is that they generated different samples. They had a human that labeled that, say, okay, this is positive and this is not. And based on that annotation that the human gave them, what they did that they updated the reward function. It's in the reinforcement learning. So they updated the reward function based on human annotated data. Based on that reward function, they also updated their policy function. Yes, and the policy function is the language model. Yes, so basically if you have a reward model that says this is positive, and based on that you update your policy model, basically you're updating your language model towards generating positive sentences. And because it is kind of all of these are not in detail discussed in the papers, out of the scope of the paper, so if you're interested, then I really encourage you to read those papers. They are very interesting. And the last one, which is compared to the first two baselines, is not as strong as the first two. It's called a weighted decoding baseline. This technique actually is the same as the GPT-2, the baseline, the unconditional language model, but in their output is weighted in the direction of directly maximizing the attribute model. What does it mean? So, for example, for the bag of words, topic, if you want to generate topic specific text, then you have the probability distribution of T+1, which is from your GPT-2, your unconditional language model. You update that probability distribution with an indicator function, which comes from, like, indicator function is 1 whenever that word is from your list of words that you defined for topic politics, for example. And you update that distribution towards that. Yes? So you give the keywords from politics a higher chance to be selected, kind of, if you want to interpret it that way. And for the sentiment, the same. So basically, you update the underlying language model probability distribution with the product, like you multiply that with the probability of that text being positive based on your attribute model. So you basically change the outputs directly. Okay.
That's how it's until now.
True. And they set it to 10 for bagel words. Yeah, correct. Cool. Okay, moving on. And then this is basically like some samples. And the samples that I show here throughout the paper, they are like lots of tables with complete sentences. I basically selected parts of the samples, and I'm showing it here. It's not the complete list. Neither the sentences are the same. Like some parts are, I removed those for the presentation. So if you're interested, please refer to the paper and look at the complete generated text. The first sample is generated by the GPT-2. It's unconditional generation. And the underlined prefix, like the underlined text, is the prefix. It's the one that we start with. It's given to the language model. So it is about the issue focused on the way that the city's police officers have reacted in recent years. Now you want to generate with the same prefix something about politics, and PPLM created this. The issue focused on a single section of the legislation. As you can see, it right away gets to it. It's talking about politics. And the words that are relevant to that topic, politics, are highlighted here. The same for science. So if it's about science, you can see words like quantum mechanics, question, solve appears a lot in their text. The issue focus on a single piece, the question, what is the meaning of life? Okay. Who knows? And very coherent, exactly, yeah, I like that. And these are just samples, and they also report the qualitative results of their their topic control task. So these are the averages, the results that are here, averages over all the samples that has been generated. The first column, so in the first basically part of the table, you can see the ablation study, BR, BC, and BCR. And the second part is the comparisons between baselines, or the other two methods that we talked about. And the topic relevance, that is, the values in this column shows the topic relevance evaluated by human. So these are, this shows that BCR and BC have like a huge improvement in compared to B and BR. So it shows the effectiveness of their model trying to generate more topic-related generation. And the topics that they had was 7 topics that I listed here. They also reported the perplexity and distinct n-grams for unigram to trigrams for the automatic evaluation of the fluency of the text, as well as the fluency evaluated by human. And the interesting part is that all of these numbers that are with regard to the fluency of the text, we can see they are almost the same. They are very close. So of course, there is a small changes, but it shows that with huge improvement in the topic relevance, and also almost they kept the fluency of the text. So, any questions on this before we move on?
Three
Yeah.
boxes?
Yes.
Could you remind us again what the 3 boxes are?
You mean this box, this box,
Correct.
this box? This is for the ablation study, which means that GPT-2 with the B is GPT-2, BR is GPT-2 with sampling and ranking technique on top of it. BC is PPLM, and BCR is PPLM plus sampling and ranking. So this is for the ablation study. And this CTRL is the technique by Salesforce, the control language model.
So they had to use it on different data sets? That's why they're... Good question. Because if they didn't train it.
Yes, but what do you mean by data set is that, let's say the idea is that they had 7 topics, yes? I think they mentioned that 2 of these topics, they couldn't match directly with the control codes in the CTRL, but the rest, let's assume politics is there. I think military wasn't there.
So that's why.
So
okay.
they gave the politics code with the issue focus to CTRL and let it generate the text. It generated the text. PPLM also generated the text. They gave the pair to the human annotators, and they selected which one is containing that attribute. And they calculated how, like basically the fraction of the times that each of these models have the controlled attribute divided by total number of samples, and they got these percentages.
Similar for the bottom rows, right?
Exactly. So WD is the weighted decoding technique that we talked about here. This one is only used for sentiment, the second baseline in these bullet points, that it's only used for sentiment, and they only generate positive sentences. So there's no way that we can directly compare that. Yeah. Yes.
The baseline,
yes.
The way you incorporate for politics, for example, is by directly using that as an input.
Not for the, okay, so for the CTRL technique, we have to directly tell the model that we want to generate a text on politics. Okay. But for our PPLM, we have an attribute model for politics, which is a bag of words model that we talked about. And then it generates the text on politics.
Baseline, just let it run freely, so you don't condition it on anything. For the B, for the first row, right? Okay.
For the first 2, yes.
Okay.
Yes, exactly. It's just, yeah, go ahead.
I thought for PPLM you just used a different set of keys and values.
By
pertaining to the politics.
A set of keywords, a set of,
right.
Yes, a set of words that have politics meaning, like something, let's say legislation or vote. There is a set of keywords that you.
But that's for training.
That is your attribute model. Mm-hmm. You use that in generation to calculate the probability of the token that you want to generate being one of these tokens.
Oh, okay.
Yes,
okay,
and
so
calculate gradient and update the.
Gotcha.
You're not updating any of the weights of your language model?
Yeah.
Right.
So the only thing that you're doing ahead of time is training your attribute model.
Gotcha.
Everything else.
I had in mind, like an alternative would be having your keys and values trained and just save them for, so you don't have to wait for your second model, your attribute model to infer again.
I see.
You can just have your language model infer. That's what I thought, but this is also very smart. Yeah.
Cool.
Yeah, just now that I mentioned it, just add my point. In that way, then you would have one language model, but technically many language models, as many as keywords you saved. Anyhow, we'll talk about it.
Yeah.
Should I start writing that paper?
Good idea. Okay. I be the co-author. Moving on. For sentiment, we are showing the some samples that was generated. So the first sample is GPT-2, original GPT-2. The chicken is now out on the grill. The city has released an image of. Okay. So what if we give the same, the chicken, we want to generate a positive sentiment, and the model, the PPLM generated the chicken was delicious, wonderfully moist, perfectly delicious, and you can see, like, very delicious, yes? But I really like how good these examples are and how well this model actually performs. And if you want to generate negative, you get the chickenpox epidemic, maybe over by the flu and worse, and you all see that the words that have this negative meaning in it. The qualitative results that was reported for the sentiment task, that's very interesting because you can see something different here. And that is in the topic control task, we saw a very noticeable difference between BR and BC. But look here, like there is a lot of improvement after you apply sampling and ranking to the baseline model, and not so much difference between BR and BC. And the reason is that what BR does is that it says that let's generate our samples and pick the one that contains that attribute. However, when the desired attribute is generating something positive and you generate R samples in the original language model which does not have any idea about like the attribute, what are the chances that you create something positive? The prior probability is actually really high because you either create positive or create negative, or let's say you create neutral. But if you sample R times and then rank them based on this sentiment classifier, there's a high chance you get some positive sentiment in your generated samples. And then you choose that one, yes? But however, when it comes to topics, there is lots and lots of topics. And what are the chances that when you generate R samples and you rank that topic? Should I continue? Yeah, so I was talking about like why we see that improvement in comparison to BR and B, and why we didn't see the same thing in the topic, because the prior probability of generating a topic is much lower than a sentiment. Yeah. And but still, when you look at BCR, you can see still like there's lots of difference. Actually, the difference between BCR and BC is higher than between BR and B. So it means that use the PPLM technique, but use also sampling and ranking. Combine them, you get the best results. The same as before, perplexity and fluency doesn't change much. So it's around the same, which is good news. And they also applied an automatic sentiment classifier just for the sake of evaluation. So this sentiment classifier is not the attribute model, it's separate. They say, okay, we generated this amount of text, we want to evaluate that, let's automatically evaluate that by training a classifier on IMDb reviews and applying that and see how much we get the sentiment. So the results are just a version of the evaluation, but not by human, by an automatic model. Questions? Okay, moving on. So there are many, many interesting experiments that are reported in the paper. I picked a few of them to present here. One is the strength factor of the attribute. You remember that alpha that we talked about, that we say that is the step size, and it works like a control knob. If you set it to 0, you are basically saying no attribute, just underlying original GPT-2. And when you increase that, you will get more and more like attribute related kind of text. So that is like basically what is the effect of increasing that number. So the first one is 0, like the strength factor is 0. The potato or potato chip is one of the best-selling snacks in the world. And then when you change that to that strength factor to 0.001, you can see that already it is generating science towards the science topic text, and says the potato tuber of the carrot family, can read the rest, but you don't see any of the specific keywords, like any of those keywords that we said in the Bagovers model appearing yet. Increasing that to 0.1, you get the potato was once thought to have no health problems, and you see fact and research appear in the text as well. What if happens if we keep increasing that? The thing is that if you keep increasing it a lot, then what you get, like if you like 0.5 and 0.1 is like a lot here, because as you can see, it right away generates something like scientists, but then gets to lab experiment and experiment, because the update is a lot. Yes, yes.
Yeah. This is when the mouse on top of the mammoth loses control and goes crazy.
Yes, exactly.
I've had that sentence over my experiments in my PhD.
Yeah. Very interesting. Okay. Odd combinations. They reported lots of odd combinations. What happens if we if we combine something, a prefix, like the pizza with the topic religion? Can it recover? Like, we don't expect pizza appear in religion topic, but still the model was able to get there, well, in a funny way. So the pizza has become a symbol of love and God, or the potato, an ancient food, is considered a sacred plant. Yeah, but it's still get there. There are lots of interesting samples in the paper, so please. Cool? You all read that? Moving on. The next experiment is about early stopping to prevent sample degeneration. And that happens when you are generating a long text. In the first 20 steps, it's moving like you're shifting the latent representation towards the desired attribute, which is like, for example, being about science, and you're doing a good job. But then after a while, after 20 steps, if you keep updating that latent representation, you will again face this degeneration. You will see experiment a lot. However, they suggest early stopping. Look, so after 20 steps, if you stop, then you will see like a much more coherent and fluent text. And that makes sense. So you're already on the part of the latent space that has that science. So you keep generating. You don't need to move again and again. Oh.
Step?
Sorry, this means?
Is that just like each word?
20 tokens, yes. So after you updated and generated 20 tokens, you stop. Like you stop updating the hidden, which means that you keep that hidden and go on. Then you don't apply the backward step anymore.
So you kind of turn PPLM off after.
Yes. Yes. Yeah. Thank you. Okay. The use cases of this model, there are many interesting ones, but one is about language detoxification that they mentioned in the paper. We saw those research papers that they tried to trigger the language models to generate toxic and racist text, yes? So there are papers that shows that if you trigger or give as a prefix to the language model words like blacks, Asians, and Jews, it will generate toxic sentences. And the reason is that a language model is trained on large corpora, and then all of those large data sets contain these type of toxic sentences, and the language model learn from them. So what if we actually, in our attribute model, we define it as a detoxification attribute model? We say give, like we want to have non-toxic, so give low probability if the sentence is toxic, so it moves towards the negative gradient, and basically it says that like if your classifier is a toxicity classifier, what happens is that it generates it says that this sentence is toxic, so move towards the negative direction of the gradient, and eventually you will detoxify the generated text from that point. So that's basically the language detoxification. However, there is a very interesting counter-argument to this, and say what prevents people to actually move towards the opposite direction of the gradient and generate more and more toxic sentences. Well, that can happen. But then the author said that, well, they hope that the value of this type of research is more than its risk, and actually this type of risk is applicable to any type of machine learning and language model. It's not specific to this technique. So,
what's the actual model for this?
A toxicity classifier, which means that given the text, it will tell us whether the text is toxic or not. Is it racist or not? And if it is, we move towards the negative of the gradients, and we generate text that is not toxic. Yeah. Yes.
Could it deal the same way with the bias? So, for example, I'm not sure like if it's actually solved, or like there were some papers about the bias in the language models. For example, when we like have like a sentence generated by it, like could this? I probably guess this the PPLM could deal with the bias also, right? Like, yeah.
Yeah, hopefully. Like, I mean, they didn't test it, and to be honest, maybe it's a very good discussion point as well. Like, I don't know if you have a gender bias or other types of bias, it can recover. But hopefully, yes. I mean, if you have a good attribute model, good classifier that detects bias, then we move in the opposite direction, and hopefully it will be unbiased. Sorry. You had a question?
Yes, we're on it.
We're on it. Okay, cool. Moving on. So this table actually shows the results of the language detoxification that they use. Is that, as you can see, the first numbers, the first column with numbers is the original GPT-2 model, and then the percentages are how many, like the percentage of the generated text that was toxic or biased. And then the second, well, in this case, sorry, only toxic. And in the second column, it's the number in percentage after PPLM applied and detoxified the text. And the third column shows the p-values, which are like how significant is the change, how significant and how successful was PPLM in detoxifying, which we can see that in average, in total numbers, it was significantly, statistically significant in detoxifying the text. Okay. The next, and I'm jumping to another use case now. It's about skeleton story generation. What is it? Is that if you have a layout, you want to help generate stories, and you have a layout, and the beginning of each section or beginning of a sentence is given as a prefix, and then the rest is blank, which you use a PPLM method or any other natural language generation method to generate the rest of the text. So in here, in this case, the layout is given and the topic is fantasy. And as you can see, all these prefixes that are underlined, these are given, and the rest is generated by the model. And we can easily see that spirit, demon, magician appear, and it can be used as a tool for story generation when the skeleton or the layout is given. Cool. So there are many interesting points about the paper. I really enjoyed it, but in what we talked about, and there are lots of comparisons. You can please, like if you're interested, I encourage you to read the whole paper. But in the conclusion, what we covered in this presentation was we introduced, like here in the session, the PPLM by the Uber AI. It is a plug-and-play language model, which means that the language model will not be changed. It will not be fine-tuned. It will not be retrained from beginning. No weights or changes. We just plug an attribute model at the generation time, and we generate text with the desired attribute. The experiments show that it has great capability of generating the desired attribute while retaining the fluency. And there are a couple of use cases that we talked about, language detoxification and also controlled story writing, and we saw the examples of those cases as well. Cool. Thank you very much. Thank you.
All right, thank
cool.
you.
Thank you.
So before I ask you guys to go home, a couple of announcements. Amir mentioned, what was that?
No questions?
Oh, no. That's right. No questions? Thanks for reminding. Oh, does anyone have it related to the paper?
I coincidentally do.
You do? Okay.
Yeah. Okay, so one point. First of all, amazing presentation.
Thank you.
And amazing paper. I really enjoyed it. One point I think it's worth mentioning, but I think the most important, like the elephant in the room, is that this reduces the parameter search to a very much like we're talking about reducing billions to, I would say, a few thousand. I'm not sure what the
exactly
parameter
a few thousand.
search is
Yeah.
for. So that's one. That's amazing. You don't have to retrain anything. Get rid of all those AWS GPUs. Second, it was very interesting to note that it would change subword information of the words, right?
Yeah.
It's also very powerful. You know, things that humans do all the time, and that's because GPT-2 uses the BPE, right? If they use the default one, they're probably using the byte pair encoding.
True.
So only two of the things that I was, you know, impressed with. Right?
Thank you. Yeah, great comments. Thank you.
Okay. So two announcements. Amir mentioned some of you guys paid for the event, but if you go to the AI.science, members.ai.science.
AI.science/register or members.ai.science.
Or if you go to the website, there is a member area on the menu too. So like you can do that. If you sign up and register for the events, like the paper discussions, through the website, it will waive the fees that non-members have to pay for it. The other announcement is sometimes the organizers, along with other people, after the talks, they go for a drink. Anyone who is up for it, please join us after we are wrapping these equipments up. Yeah, that's it. Thank you so much.
Do we mention those online as well? Should I go over them?
Are you still live?
Sure.
So we're gonna cover the discussion points too. If you're wrapping up, read the point, man, please.
So just quickly go through them and then. So the discussion points was that they used A/B testing for the human evaluation, and they showed a pair of sentences and asked which one, or neither and both. Does it is the right choice for evaluating attribute relevancy? Are there any other approaches for asking for human evaluation that could be better, or maybe no? But just that's the discussion point. What other NLP tasks could this paradigm of latent space perturbation be applied to? So by this technique sounds like a very nice way of preventing lots of computation time and updating lots of parameters. So where else it can be used? We saw a couple of them, like detoxification and story generation. Other comes to mind, and why there is a noticeable difference between the external sentiment classifier and the human annotations. And I noticed it here in this table that it gave here. Based on the sentiment classification, we can see there is a huge difference, especially here in the comparison of the baselines, WD and GPT-2, the fine-tuned reinforcement learning-based one, that the human annotation said 30% sentiment relevance for this model. However, the automatic version said 77%. There's a huge gap between these two types of evaluation. Why we think that happened?
I have a guess for that.
Yes.
I was thinking of when you were presenting it. I think that there may be similarity in the training sets for those other models and the classifier that was used to evaluate sentiment that is different to the training set that was used to build the classifier that was used in the plug and play.
But the samples that are generated by GPT-2, the FT-RL or the weight decoding one, the competitors, they are not. They are pre-trained versions, and we use them to generate positive sentences. Yes, the humans label them as not that effective as our automatic method says. We don't train them, but probably you're saying that the training data that they train their model on is very different than the training data that we use in sentiment.
Yeah, I just think like for instance the Salesforce model.
Yes.
They probably made their sentiment, like whatever they were trying to optimize in sentiment was similar to the one that we use the IMDb pages, the external classifier.
Oh, okay. So that's
like that seems so high. there's probably an overlap in the
I
training
see.
set, and that's why I think maybe a similar reason why there is.
But if the automatic version was low, that was a good point, because it means that the trained data sets are different, but the human evaluation is low. So you know what I mean? Like,
so the training set should be similar, no?
training set should be similar then.
Yeah.
Yes, that makes sense. But if it's different, then it should be lower.
Actually, when you were mentioning this, I thought about it. And it probably links to one of the first discussion points too. Maybe because it is a comparison between GPT-2 FTRL and PCR.
Yeah.
Probably the manual annotators saw the contrast more, and then they chose PCR. And that is probably where the difference in numbers are coming
first
could be.
with regard to first discussion point.
Yeah.
Okay. So it's the way that the human evaluation was done that might have affected. That's Royal's point, basically. Yeah.
Did they do any? Did they do any inter-annotator sort of agreement?
No, I mean, I'm but saying no. I mean, they didn't report it. Maybe they've done it.
They did get three annotators per sample.
Yes.
Yeah. They did make sure they had coverage, but I don't think they did. They didn't report any actual agreement. Yeah.
But each sample is annotated by 3%, and they took the
majority.
average for fluency and maximum voting for relevancy.
This idea of A/B testing, I think they were borrowing it from another paper. So I should probably read that one, but otherwise we couldn't
Did you
really.
just sign up for another talk?
Well, I don't know if that one's
That's
trending.
very
It's older, but yeah, we couldn't quite figure out why this A/B testing paradigm was, why it was chosen really, and why they didn't just have samples shown on their own. It seemed to introduce the potential for an unnecessary bias by putting two samples side by side, and as Royal was saying, sort of just automatically creating this contrast between them. So it might be, maybe both samples would be positive, but in seeing them together, one is more positive, and so that biases you towards how you label. Anyway, it didn't seem to be any clear reason to do it this way, so we didn't understand why they did it.
I mean, they didn't seem to have created that contrast because of the point that you just mentioned, right? It could be both, it could be neither, and that doesn't really...
And they give the option for the annotator to say both or neither. They do give those options, but it felt like you could have just had each sample on its own and it would have worked just as well or better.
So the users might have their own biases while marking both or neither. They might, especially for neither, they'll be like, okay, what am I doing here annotating? Probably there is one of them, you know.
I think for A/B testing or for like ranking, sometimes they give you multiple, like 3 or 4 things, and they ask you to rank. The like goal of those types of things is to establish a robust ranking of all the things, and not necessarily like an absolute thing that can be compared to something else.
Good point, but
So,
in this case they weren't using it like
exactly.
that.
So I think that they may have used this because it was useful in some. It is like more robust to having things ranked correctly, but it doesn't translate very well to absolute comparative numbers very well. So yeah, I would have been confused by this choice too, given the way that they used it as a baseline comparison.
I have a question somewhat related to the second point. Why does perturbing the latent space work better than competencies?
I think. Yeah, exactly, and yeah, of course. Basically, you're directly changing the probability distribution at the word that is gonna be picked is different rather than updating that return representation that contains all the information for the previous tokens as well, while you are exactly the essence point. Yeah. Yeah.
Okay.
All right, thank you very much. Thanks a lot.
Thank you.